Hi guys, welcome to my YouTube channel. Today we'll be dealing with strength of materials and structures N6. This is the first topic, which is thick cylinders. Here we have 4 of the graphs that are going to be needed in every calculation that we'll be dealing with. But this topic has actually 5 graphs, and we're gonna be dealing with the last graph on the next video. So let's start. First, we have the internal pressure graph. This internal pressure graph is when a thick cylinder experiences pressure internally. When a thick cylinder experiences pressure internally, it experiences this, and then we express it in graphs in this manner. So the radial stress is positive and the hoop stress is negative. What you need to know is that when they say the internal pressure is 30 megapascals, it is actually your radial stress max. Your internal pressure is equals to your radial stress at maximum, not at minimum, because at minimum it's 0, and then at maximum is the quantity that you're gonna receive the internal pressure in. Maybe it's gonna be 40 megapascals, maybe 35, depending on the question. So the key word that will show us, or that will give us a hint of which graph we're going to use, because there are going to be many graphs that we're going to be dealing with. The key word is subjected to internal pressure of a particular magnitude, like 30 megapascals. So we're going to have small letter d and big letter d. Sometimes we have also DC. DC is experienced in when the graphs are compound, meaning when the thick cylinders are compound. That's the only time where we'll have DC. But when it's one cylinder experiencing internal pressure, we will not have DC. Therefore, I would like to write this in a dotted format. Sometimes you are going to have DC. You see, I already indicated DC here. So that's done with internal pressure. Let's go to external pressure. What you need to know about this graph is that it has a trick. It has a trick, right? But nonetheless, it also has its easy spots. Get this. The hoop stress and the radial stress are positive. Always. They are positive. But that doesn't change the fact that there's a law that we're going to be using in this topic, which is Lehm's equations. Right? It doesn't change this. No, it doesn't. Nonetheless, I've not introduced that yet. Let's continue with the graphs. You see, when it comes to the internal pressure graph, the key word is that they will tell you, they really tell you that the internal pressure graph, the internal pressure is 30 megapascals, for example. And then what you need to know is that this value must be positive. It must be positive because it is experiencing an external pressure. It must be positive. So that's the only trick here. And then the other trick is that you see when we on the internal pressure, the small diameter is this side, right? On this part. If you can notice, this part is actually this part, just it's flipped, right? So the diameter on this one, it's here, and then this diameter is here. But on this part, it's not the same. You can actually see it because when you check this part, right, this part, the small d is here on the radial, you see. But on this radial, the big diameter is on this side, you see. This is why I indicated it in the red marker, you see, so that you can know that. This is the trick of external pressure. That's the only trick. If you can actually substitute correctly here and there, you're gonna get everything correct. Because in this topic, we're only gonna use Lame's theory, you see. Nonetheless, let's continue. Shrinkage graph. Shrinkage graph has something in common with the resultant graph. It's that the radial stress at these points are equal in both sides. So there's the inner cylinder and then there's the outer cylinder. This one, it only happens when two cylinders are shrunk together. So guys, if they say shrinkage graph, this is what they mean. If they say a copper is shrunk into a steel cylinder, this is what they mean. It's this process. Sometimes the length is equal, sometimes the length are not equal, but it's non-examinable. They won't examine the fact that the length, they won't examine it. But get this, what is examinable is this part. You see this part, if you can manage to ignore this part, if we can ignore this, I want to show you something, guys. If we can ignore this, you see, we have only one cylinder, right? And this one cylinder that we have, I want to show you something. It has two diameters. It has this diameter and this diameter. So this is the hole inside the cylinder. So this is the cylinder, this is the hole in the cylinder, right? So this diameter, let's say it's 20, and this diameter, let's say it's 30. This means from the center to here, it's 10. From the center to here, it's 15. So this is the cylinder in and of itself. So now we are pressing by force. We are pressing this shaft into this shaft. You see? So when we are shrinking them together, what you'll realize is that there will be a force here. That pressure that this experiences and this also experiences, because we are forcefully engaging them. That thing that they're gonna feel, what we call it is pressure. So there is going to be shrinkage pressure. And shrinkage pressure has a graph, which is the shrinkage pressure graph, right? So this diameter, the outside diameter of this shaft is actually equal to the inside diameter of this one. Remember, it's actually like this. So this inner diameter is equal to the outer diameter. You see? So that's it. This is why when we're drawing the graph, we don't have 4 diameters. No, because they share one in common. So get this. We don't have 4, right? Because they share one in common. Get this. We have one, the one they share in common, and then we have this one. You see? I did a small sketch here explaining why and how, but guess what? It wasn't necessary. We already have this. So this will only help you with imagining it, and then also with you knowing what's actually happening. You won't be needed to draw this. You don't need to draw it. You just need to understand it. That's all. This is what you will need every time you're attempting this question. Shrunk two cylinders together, you get a shrinkage graph. So this is actually a phenomenon that happens when two cylinders are shrunk together. Shrunk together like this. Shrinkage. Because this exerts a pressure on this exerts a pressure on this. You see? Nonetheless, let's continue. RC is actually radial stress at a common diameter, because this is actually the common diameter. It's common on the inner and on the outer. It's basically the same, right? So if they're gonna give you, let me show you an example. If there's a cylinder that is, let's say, 100 millimeters, you see. So from here to here, it's 100 millimeters, right? And then it has its inner diameter. This is outer diameter. It's the outside. Then this is the inner diameter. It's the inside of the same cylinder, right? Normally, it's going to be something like this at the end. Nonetheless, this is the inner diameter, you see. When you're going to fit something in a cylinder, get this, you're going to fit it here, right? So the cylinder will have to share the same diameter here. The cylinder that's going to enter here, it's also going to have this D. And this D is equal to this D. That's why it fits, right? So therefore, we have DC. At least in calculations, that's how it is. So this is why we have DC. There and then now, that's where we also get this concept of RC. This is the radial stress at common diameter. So the radial stress here at the common diameter is equal this side and this side. So if this is 30 megapascals, it's going to be 30 this side and this side. Okay, that's the only trick here. And then, so look, what you need to know is that the resultant graph has RC. The shrinkage graph also has RC. I call it RC because it's their common radial stress. So this means at this point, the radial stress in the inner cylinder and the radial stress in the outer cylinder are equal at this point. So if this is 30 megapascals, it's also 30 megapascals on this side. So this part, it's one value, right? So what does that imply? It implies that you can use it. If I have 30 megapascals here, I can use it on this side. I can also use it on this side with the Lahm's equation. Normally, they'll give you either this or this. And then scarcely they'll also give you this. But nonetheless, the thing remains the same. Another thing that you need to know is that the radial stress maximum is equal to the internal pressure. So if they give an internal pressure of 40 megapascals, you must know that 40 megapascals, they'll tell you as the copper cylinder is shrunk into the steel cylinder, there is an internal pressure that is experienced, and that internal pressure is 40 megapascals. You're going to put it here. You see? You're going to put it here. The internal pressure is experienced at this point. You see? It is equal to this Rmax, so you're going to place it here. And then you're going to also probably have this point, and then you're going to be able to use the Lahm's equation. So the other thing that you need to know is that the key word of the resultant pressure graph is that they'll tell you there's an internal pressure. There's a resultant internal pressure. If they say there's a resultant internal pressure, just know it's the resultant graph. If they say resultant radial stress is 40 megapascals, where else can you put it except in the resultant graph? Because it's gonna have to be somewhere here. There's no resultant value here. There's no resultant value here. There's no resultant value here. Resultants only fit here. So, if they say resultant hoop stress is 40, you use this graph. Resultant radial stress is 30, you use this graph. And they're going to give you other values that you also use. So, that's it for thick cylinders, guys.